Gases are substances that lack intermolecular forces. To put this in context, solids have very strong intermolecular forces. Liquids have more fluid intermolecular forces. Gases have none. The typical density of a gas is just about 1 gram per liter. That's up to 1,000 times less dense than a liquid. In terms of their volume, they'll fill up a container regardless of the amount, meaning that those molecules are like three-dimensional billiard balls that can bounce around freely, regardless of how many there are. Frustratingly, gases are often invisible. There's no reflection plane because it fills up the entire container, so oftentimes it appears that there's nothing there at all. And the only comment we'll make about the chemical behavior of gases is that they react much quicker compared to other phases because they can mix so completely because of all that space that is there, and so that you can have a very rapid reaction for a gas compared to a liquid or a solid. Let's consider the physical behavior of gases. What's happening when you push in a closed syringe barrel? Well, the volume will go down. The pressure, you'll feel it go up. And if you do it slowly, the temperature should remain more or less constant. We can express this mathematically, showing that P1V1 equals P2V2. For example, 2 times 4 will equal 8 times 1. Note how as the pressure is going down, the volume is going up. Note also that this is the general expression for an inverse relationship. And it may not appear to be at first, but this is how you can always express something that is going in opposite directions. Let us imagine we're heating an expandable system, in this case a piston. As the temperature goes up, clearly this thing will expand. The pressure can remain constant if there's no friction, and since this is a proportional effect, they're both going up, we have to divide. We express this as T1V1 equals T2V2. This is the original conditions. These will be your new conditions. You must use Kelvin for temperature in order to have a proportional effect. You don't want to have something that can go below 0. This is known as Charles' law. You can heat a closed container if you're feeling brave. I wouldn't recommend it because as the temperature goes up, the pressure will go up. The volume clearly cannot change in this sealed container, and so the volume will be constant. This is known as Gay-Lussac's law, and it has the same form as Charles since it's a proportional relationship. This is sometimes referred to as the dangerous law. T1 over P1 will equal T2 over P2. Always use Kelvin for your temperature. Which gas moves fastest under these conditions? Well, we have a relatively small molar mass gas compared to one that's twice as big. Note that these will meet at about this point, showing that the ammonia gas is traveling faster. This was studied by Graham, who found that the small molar gases go faster, but interestingly, twice as small does not mean twice as fast. In fact, twice as small means 1.414 times as fast. He realized that this was a square root relationship, and so he expresses it like this. The easy way to say it is that small gases go faster, but not much faster. The sciencey way to say it would be that the relative rate of gases is inversely proportional to the square root of their molar masses. How's that for a mouthful? Interestingly also, Avogadro found that gas atoms all have about the same volumes. Since it's 99% plus space between the molecules, the actual identity of those little dots, if you will, is relatively inconsequential. So if you have the same number of molecules, whether it's argon, nitrogen, or hydrogen, and here we express them as a mole's worth, right? That's a mole of argon, 6 times 10 to the 23rd atoms of argon. Similarly, that many molecules of nitrogen or molecules of hydrogen, they all occupy the same value, and it's given as 22.4 liters. But be careful, because we have to fix the temperature and the pressure, since that will change things. And we've arbitrarily defined standard temperature and pressure as 0 degrees Celsius, that's 273 Kelvin, and 1 atmosphere. And under those relatively cold conditions, notice that's not room temperature, the volume of any gas will be very close to 22.4 liters.